Hey, welcome back to Fat Mama Physics. This is the continuation of nuclear energy levels and radioactive decay, as well as pair production and annihilation. So I am just going to do question number 2 for us. So pair production and annihilation, hopefully you got a little bit of that in the SL portion. So what that means is if you have a particle and an antiparticle, they come together and they annihilate, meaning they will produce light or energy for that matter. Or if you have a photon of light, technically 2 photons of light coming together, producing you a pair of particle-antiparticle together. Okay, so we are going to do example 2. So given that the total energy is this one, and what this means is your mass gets converted into energy as well as whatever kinetic energy your particle had already. So it's the energy associated with the mass and as well as its kinetic energy. Now, when we're talking about the longest wavelength of light that could be produced, this is talking about, if we take a look at the Planck-Einstein relationship, the longest wavelength corresponds to the lowest energy produced. So it's not necessary, which means that, sure, the electrons and the positrons are going to have a certain amount of mass. That's not going to be able to change. What could change is the amount of kinetic energy it goes into this annihilation, which it could be 0 to give us the longest possible wavelength. Okay, so don't forget, there's a 2 here showing the fact that there's going to be 2 particles involved, an electron and a positron, in which they're going to annihilate, and these photons produced, these 2 photons are going to share the energy produced by your electron-positron pair. So that's going to look like the following. Essentially, you're going to go from mass is going to turn into energy, and this energy is going to turn to some photon of light, which will produce a what we'll do, I guess, wavelength. Okay, so frequency or wavelength for that matter. Okay, it's going to associate with a photon. So to get us our energy, we're going to look at the mass of an electron, which is going to be exactly the same as its antiparticle, the positron. So we are going to do, this energy is going to be 2 times the mass of our electron times the speed of light squared. And this is going to get divided amongst our 2 photons of light, which in which each of them are going to have some sort of energy associated with their photon, with the photon. And funny thing is that this 2 is going to kind of go away, because we got 2 particles to begin with, 2 particles that we end up with, and of course this energy of a photon is associated with Planck's constant, speed of light, and the wavelength of light emitted, which is what we want. Okay, what is the longest wavelength of light emitted? So we essentially have me, the mass of an electron, times speed of light, is equal to hc over lambda. So if we solve for lambda moves on top, we're going to have hc over mass of an electron times speed of light squared. So putting in the Planck's constant, the speed of light, and the mass of an electron, which is 9.11 times 10 to the power of negative 31 kilograms. I'm silly. I could have just used 1 speed of light, but this is speed of light squared. Okay, so one of them do cancel out, which then this gives us, running out of space here, 2.4259, and rounding up to 2 sig figs, this is going to be 2.4 times 10 to the power of negative 12 meters. Okay, so that's an example with annihilation. Again, we're going back to the Planck-Einstein relationship. Okay, so Planck's-Einstein relationship kind of opens the doors to all sorts of topics, which is why this lesson here bled in with some little loose topics. We're just tying the knots together. So, thank you for sticking with me for the second part of this video, and I wish you the best of luck with your practices. And Fat Mama Physics signing out.